Hello and welcome to this video tutorial. Today we're going to look at the solutions for physics homework number 42, gravitational and elastic potential energy. We will be working questions 12 through 18. Remember, gravitational potential energy relates to an object's change in height. Okay? Spring potential energy or elastic potential energy relates to the stretch or compress of a spring. So for these problems, you might need to use two different formulas in combination. Spring force equals the spring constant times the stretch or compress of the spring. And the energy stored in a spring would be the spring stretch or compress squared, delta x squared. Now I'm just going to put x, not delta x. I don't usually write delta x, but x, when I put x, that's the same thing as delta x here, times the spring constant, and then take half of that. All right, so let's begin. Number 12. A 5 kilogram mass is initially sitting on the floor when it is lifted onto a 1.15 meter high at a constant speed. How much work is done in lifting the mass? Okay, so this question was kind of sort of done in physics homework 41, but it was sort of worded in a different way because it was, well, let's just say part A was found in physics homework number 41, and now part B and C are kind of the new development in how do you connect work to potential energy. So recall, gravitational potential energy is the potential for gravity to do work. Okay, so what we're going to do is we're going to essentially be looking at this relationship, mass times g times height. If you look at the picture that we drew over here to the left-hand side, you can see the table is 1.15 meters high. So how much work is getting done? Well, work, if you recall, is a parallel force times distance. And when you lift this weight up, especially at a constant speed, the weight is balanced by the uplifting force. Okay, meaning what are you lifting? You are lifting essentially the weight of the object. So I can replace this with the parallel force becomes m times g times d. Okay, now I'll go ahead and plug into it. Okay, mass is 5 kilograms. So we're going to go 5 kilograms times 9.8 times 1.15 meters. All right, let me just take a second to draw my answer box. Sorry, I like having an answer box to organize my work. There we go. Okay. Take a second to put this in your calculator. You're going to go 5 times 9.8 times 1.1. And if you do that right, you should get about 56.4 joules. Now, part B, it says, what will the gravitational potential energy be of this mass relative to the floor once put on the table? So, well, what is gravitational potential energy? It's equal to the work you do against gravity. The work you do against gravity, which, by the way, you already did, right, is equal to the potential energy that you gain. So in other words, right, 56.4 joules. All right, but now part C, it says, what was the initial gravitational potential energy relative to the floor while the mass was sitting on the floor? Well, we can go mass times g, but what is the height if you're sitting on the floor? The height is 0, right? So that means we end up with a potential energy of 0. Number 13. A crate which has a mass of 48 kilograms is sitting at rest at the bottom of a frictionless inclined plane of length 2.85 meters long, which meets the horizontal at an angle of 31.5 degrees. A force is applied so as to push the crate up the incline at a constant speed. Part A, what will be the magnitude of the force F required to push the crate at the top of the incline? B, how much work will be done to push it up the incline? C, what was the height of the incline? And D, what was the gravitational potential energy when it reached the top of the incline? So, okay, let's take a look at the force required to push it up. Well, remember, it's frictionless, so we don't have to worry about friction, but here's what we do have. You have normal force coming up, you have the force going up the plane, you have the weight going straight down. Recall, you need to get the components of your weight. So you can see that my gray component balances the normal force. But if you also remember, my blue component here, right, goes downhill, and it's my blue component that balances the applied force going uphill. Okay, and that would be, if this is angle theta, that means the blue component would be mg times the sine of theta. So part A, F is going to balance mg sine of theta. Okay, that's what we're going to plug into. Okay, the angle was 31.5 degrees. The mass was 48 kilograms times 9.8. All right, please take a second to put that in your calculator. Okay, if you did this right, you should be getting about 246 newtons of force. Okay, now part B, we're looking for the work to push it up the hill. So work is equal to a parallel force times distance. Well, the parallel force, if you can see, is the force that's parallel to the incline. It's the force pushing it uphill. Right, which would be 246 newtons times the length of the incline, 2.85 meters. Do this right, you should get about 701 joules. Okay, part C. Do that over here. So part C says, what's the height of the incline? Well, if you see over here, you have a right triangle, right? And the height is just the opposite side of theta from that right triangle. So if you know about how we've been using our components of a right triangle, the opposite side links to the sine, right, of the angle. It's connected to the sine of the angle. So the height is really what? Length times the sine of the angle. That's what we're going to be using. Okay, so we're going to go 2.85, right, times the sine of 31.5 degrees. Okay, please take a second to put that in your calculator. And you see we get about 1.49 meters, almost 1.5 meters tall. Okay, now part D is saying what's the gravitational potential energy of this crate? Well, gravitational potential energy, if you recall, is m times g times h. And that's what we're plugging into. Okay, m would be the 48 kilograms of mass times 9.8 times the 1.49 we just entered and found for height. Okay, put that in your calculator, please. And you should be getting 701 joules of gravitational potential energy. So again, based on what we said earlier, okay, we're now verifying it mathematically. What did we say earlier? The increase in gravitational potential energy, because the gravitational potential energy on the ground is 0. So 701 is actually the increase in gravitational energy from 0. So the increase in gravitational energy is the same as the work that's done against gravity to bring it up to that height. Remember, gravitational potential energy is the potential for gravity to do work. Well, it's going to be balanced by the work you actually do to bring it up to that point. Number 14. Suppose you have a mass of 62 kilograms and you walk up a staircase which has h equals 12 meters and length equals 15 meters deep. How much work do you do in walking up to the top of the stairways? Well, the length really doesn't matter, because when you walk up a flight of stairs, it's all about lifting your body weight up each stair, but each stair is just a fraction of the entire height. Okay, and what are you doing? You're doing work against gravity to bring your body weight up to a certain point. So, in other words, part A, right, is a parallel force times distance, but what are you doing? The distance would be the height. The force would be you applying a force against your body weight to bring yourself uphill. In other words, m times g times h. Okay, so we're going to go 62 kilograms times 9.8 times a height of 12 meters. Take a moment to put that in your calculator, please. You should have gotten somewhere in the neighborhood of about 7,290 joules. Now, part B is looking for the gravitational potential energy when you reach the top. Well, what is the gravitational potential energy? It's the same as the work done, right, against gravity, which we just found. 7,290 joules. So in our last few questions here, we are going to be taking a look at a combination of spring forces. Spring force is proportional to not only the stiffness of the spring, which is the spring constant K, but it's also proportional to X, the distance you stretch or compress a spring. So we will need to use this equation every once in a while. But the actual energy stored in a spring is 1/2 times K, the spring constant, times X squared. Okay, so a couple of things. Make sure that you have things in the right unit. If you see centimeters, remember to convert those to meters. If you see grams, remember to convert those to kilograms. All right, number 15, let's read. A force of 35 newtons is applied to a spring, and as a result of the spring, stretches a distance of delta x 12 centimeters. So I just got done saying change it to meters, right? So that means this is going to be 0.12 meters. Okay, so part A is looking for spring constant K. So what I'm thinking is, let's see if we can use this. We've got the F, we've got the X, right? We're looking for the K. So we just got to solve that equation for K. So F spring force equals Kx. You'll notice to solve for K, we just have to divide by X. So K is equal to the spring force divided by X, the distance it stretches. And you guys are going to go 35 newtons times 0.12 meters. Please take a second to put that in your calculator, please. All right, you should be getting about 292. Now the unit would be newtons per meter. That's the unit of K. Okay, there's part A. Now part B, it says how much energy is stored in the spring. Well, that's where we're going to be using the other equation. So the potential energy in the spring, right, is going to be equal to 1/2 kx squared. Well, now you have K, so it's an easier thing to substitute into. So K was, if you remember, 292 newtons per meter, and you are substituting 0.12 in for the distance the spring is stretched. Okay, please take a second to put that in your calculator. I might suggest you put this in your calculator just like you do kinetic energy, meaning square the x first, then multiply times k, then divided by 2. If you take it in a series of steps, it's pretty easy to put in your calculator. Well, if you did this right, you should be getting about 2.10 joules. Number 16. A spring which has a spring constant of 120 newtons per meter is stretched to distance delta x equals 15 centimeters by a force F. Part A, how much is that force F? B, how much energy is stored in the spring? So again, just like in the previous problem, let's turn that into meters. Okay, so how do we find part A? Well, F equals K times F. Spring force is K times X. K, as you can see, is 120, right? Newtons per meter. Okay, and the stretch is going to be 0.15 meters. You can see how the units cancel, giving you the correct unit, right, of force. Please take a moment to put that in your calculator. Okay, if you did this right, you should be getting about 18 newtons of force. Okay, part B. How much energy? Okay, well, we're talking about elastic or spring potential energy. 1/2 K times x squared, that's what we're plugging into. Okay, well, K we saw was 120 newtons per meter, and X was 0.15. So you're plugging in the same stuff, but into a different type of relationship. So again, start with 0.15 squared, then times K, then divided by 2. Go ahead and take a moment to put that in your calculator. And if you did this right, you should be getting about 1.35 joules. All right, number 17. A spring which has a spring constant K is hung from a ceiling as shown to the right. You can see the picture right here. A mass of M equals 3 kilograms is added to the end of the spring and then slowly lowered until equilibrium is reached. At this point, the bottom of the mass has been lowered a distance of delta H equals 52 centimeters. Okay, I can see right away we're going to need to change that. Okay, that would be 0.52 meters. Okay, something to note if the height changes for the block, that's also the same distance. This right here, that delta H is the same as delta X. That's the same as X, sorry, not K. That's the same as X, the distance the spring stretched. So the height it's lowered is the same distance as how much the spring got stretched. So it says part A, what is the magnitude of the force exerted by the spring when it reaches equilibrium? So equilibrium, if you recall, means what? Means no acceleration, forces are balanced, right? Newton's first law, forces up equal forces down. So if I go and look at the picture, okay, I'd have weight equals mg going down, but then I'd have spring force, right, equals k times x going up. So essentially, if I'm looking for the force exerted by the spring, notice, guys, I don't have k. I've got x, but I don't have k, so I can't solve for the force exerted by the spring yet. But I can indirectly set the spring force equal to the weight that it's balancing. And that's exactly how I'm going to solve this part A. The spring force is balancing the weight, which is going to be 3 kilograms times 9.8 meters per second squared. Okay, plugging that in correctly, you'll get about 29.4 newtons. Now, part B is looking for that spring constant, so now you can take that same equation, but set it equal to kx, and when you solve for k, you have to divide both sides by x. So it's the spring force divided by x. The spring force being 29.4 newtons. Okay, x is the same as how much the height got lowered, 0.52 meters. Okay, take a moment to put that in your calculator, please. And if you do this one right, you should be getting a spring constant K of about 56.5 newtons per meter. Part C, how much energy is stored in the spring? Well, we're talking about elastic or spring potential energy. So 1/2 K times x squared, right, is how we do it. And now you have everything to substitute. The K we just found, 56.5 newtons per meter. And x, if you recall, was the height difference or the distance it stretched, and that's going to be about 0.52. Okay, in your calculator, you'd want to square that first, times k, take half. Please take a moment to put that in your calculator. If you did this right, you should get a little over 7.5 joules, about 7.64 joules. All right, and finally, question 18. So we have a mass that's dropped from a height of 2.2 meters above a vertical spring sitting on a horizontal surface. So let's draw a before and after picture. So here's before. Yeah, I've got a block. All right, and the block is falling, okay, and it falls 2.2 meters, right? And then right here is a spring that it's going to land on, okay? So it's going to basically land on a spring. The spring's on a horizontal surface. That's before. Now, afterwards, what happens when the block meets the spring? Well, it's going to compress the spring, of course. So I'm going to draw the block here with a fully compressed spring. Okay, and what ended up happening? How much did it compress? It says the spring compressed 30 centimeters, which is, of course, right, x equals 0.30 meters. Now, if you take into account the height difference would be 2.2 plus 0.3. So the height, right, is the sum of the two, or 2.5 meters, okay? We'll need that. So this is how much gravitational potential energy was contained in the 5 kilogram mass before it dropped. Well, gravitational potential energy is equal to m times g times h. Okay, we're going to go m times g times h. The mass was, if you remember, 5 kilograms. G is always 9.8 on the surface of the Earth. And we're dropping it from a height. We're taking this point here to be 0 potential energy, 0 height. So that means the full height that it dropped from was actually 2.5 meters, because we're talking about the height that it dropped plus the height that it drops even more when it compresses the spring. Okay, please take a moment to throw that in your calculator, please. If you do that right, you should get about 123 joules. Okay, part B. What will be the energy stored in the spring, right, when the mass comes to a halt? So basically, the energy stored in the spring by compressing it. Well, that is your spring potential energy, right? 1/2 times k times x squared. So 1/2. Let's see if we were given the k. I think we were. No. Okay, so we can't do it this way. We can't solve it this way. Okay. In fact, if you look at part C, you're looking for k. So we can't solve it this way. But you know what we can do? I'm going to kind of erase some of this. You know what we can do? Instead of plugging directly into this equation, what we should realize is that the total energy, I'm going to do this in a different color so you can see it. The total gravitational potential energy at the highest point becomes the spring potential energy when it is fully compressed, meaning the spring potential energy indirectly is the gravitational potential energy, which we just found. This is using law of conservation of energy, right? Remember belly flop Benny? And you'll notice it's also 123 joules. All right, now part C, you have to essentially solve for k. So I'm going to take the spring potential energy equation, okay, which is 1/2 times k times x squared, and I'm going to solve that for k. So in order to do that, I need to begin by multiplying by 2. So I get 2 times the potential energy equals kx squared. All right, and then to isolate the k, I have to divide by x squared. Okay, and then we'll go ahead and plug into that. So k is equal to 2 times your potential energy, which was 123 joules, divided by x, which if you remember was 0.30, right? And then don't forget to square that. Please take a moment to put that in your calculator. If we did this right, we should have come up with a value of about 2,730 newtons per meter. Okay, kind of a high number. It means it takes a lot of force to compress it 1 meter. That means it's a very stiff spring. If it's a stiff spring, that would mean that the coil is probably very, very thick. Okay. Hope you found this video tutorial to be helpful. Okay. Remember to come on in and see me individually if you're still stuck. Pause and rewind it as you need it. See you next time.